I always tell my students that mathematical knowledge has only value when it's connected. So let's say that we have a bunch of facts. Let's say that we have fact 1, fact 2, fact 3, and fact 4. If we know them in isolation as separate facts, then such knowledge holds little value. It is the relationship that should be studied first and foremost. We can think of mathematics as of a tree. It is only alive when its branches are connected. That is why, in my opinion, one of the most valuable exercises is solving the same problem in as many different ways as possible. So in this video, we're going to explore 9 different methods for solving this problem with parameter. If you like this video, please consider subscribing and tell us in comments which of the solutions you like the most. So here's the problem itself. We have to find all values of the parameter a for which the system of equations has exactly one solution. So let's consider the solution that always comes to minds of the students. Let's consider a quadratic equation. To come up with a quadratic equation, let's multiply both sides of the first equation by 16, because we have 4y here. We will now have 16x squared plus 16y squared equals 1600. And let's write down the second equation as 4y equals a minus 3x. We can now see that this is 4y squared, which is why we can write down the first equation as 16x squared plus a minus 3x squared equals 1600. And now this is just a quadratic equation. And if we want this system of equations to have exactly one solution, then this equation too has to have exactly one solution. So let's write it down as 16x squared plus a squared minus 6ax plus 9x squared equals 1600, which results in 25x squared minus 6ax plus a squared minus 1600 equals 0. We can now find the discriminant of this quadratic equation, which is minus 6a squared minus 4 times 25 times a squared minus 1600. And we can say that since the equation itself has to have exactly one solution, then the discriminant should be equal to 0. So we have another quadratic equation, 36a squared minus 100a squared plus 1600 times 100, which gives us another 2 zeros, equals 0. So now we have minus 64 here and minus 160,000, which results in a squared equals 2500 if I'm not mistaken, and a equals plus or minus 15. And that's the answer to this question. To sum up, we use the substitution method and get a quadratic equation which has exactly one solution when the discriminant is equal to 0. And let's now move to the second method. The second solution is graphical. We consider the equations of this system as sets of points on the Cartesian plane. So let me remind you that the equation of a circle is x minus x0 squared plus y minus y0 squared equals r squared, where x0 and y0 are the coordinates of the center of a circle, and r is the radius of a circle. So the first equation defines a circle with center at 0, 0, and the radius of the circle is 10. So this is the Cartesian plane, here's x, this is y, and this is 10. The second equation defines a straight line, and we want this line and the circle to have exactly one point in common. So we don't want this line to be placed like this, because in this case we have two solutions. No, we want the line to be tangent to the circle, which means that the distance from the center of the circle to the line should be equal to the radius of the circle. Let me remind you that if we have a point and a line which is given by the equation ax plus by plus c equals 0, then the distance from the point to the line is given by this equation, ax0 plus by0 plus c absolute value. So we just plug the coordinates of the point into the equation of the line, divided by a square root of a squared plus b squared, which is basically just the length of the normal vector to the line. So from this formula we can derive that 3 times 0 plus 4 times 0 minus a, which is the left side of this equation if we subtract a from both sides, and x and y are equal to 0 because the center of the circle is 0, 0. So we have the absolute value of that divided by square root of 3 squared plus 4 squared. And this should be equal to the radius of a circle, because otherwise the line isn't tangent to a circle. So here we have the absolute value of a is equal to 5 times 10 is equal to 50, which gives us two values for the parameter a, plus and minus 50. So let's sum up. We have a circle, and a line. We want this system of equations to have exactly one solution, which means that the line should be tangent to the circle, which implies that the distance from the center of the circle to the line is equal to the radius of the circle. Here's a formula for the distance from a point to the line, so we have an equation and the answer. Now let's look at the third solution, which is also graphical. So it's based on the same idea, but this time we're going to use more of elementary geometry, because not everyone knows the distance from a point to a line. In this solution we will focus on the triangle, which is right-angled. We can find its height because the radius dropped to the point of tangency is perpendicular to the tangent line and is equal to 10. And we also can find the legs of this triangle from the points of intersection of this line with the axis. So if we say that x is equal to 0, then we have 4y equals a, which gives us y is equal to a over 4, which is the length of this leg. So it's a over 4. If we put y equals 0 into the equation, then we have 3x equals a, which means that x equals a over 3 is this leg of this triangle. So we have a over 3 here. Now we can find the hypotenuse of this triangle using Pythagorean theorem, which is equal to square root of a squared over 16 plus a squared over 9, which is 5a over 12. And now we can express the area of this triangle in two different ways. So the area is equal to 1/2 of the product of two legs of this triangle, and on the other hand it's equal to 1/2 of the product of the height and the hypotenuse. So it's 1/2 of 10 times 5a over 12. And if we solve this very simple equation, then we will have a equals 50. And similarly, for this case, when the line is tangent and touches the circle down there, we will have a equals minus 50. So we can get both the positive and the negative values of the parameter. And that was solution number 3, which uses more of elementary geometry. There are other ways to calculate the values of the parameter for graphical solutions. I showed you these two because they are the most common, but if you have other ideas in your mind, feel free to write them down in the comment section. Now let's move on to the next solutions. Now the fourth solution of this problem is also graphical, but this time, instead of looking at a circle and a line, we're going to be looking at a circle and another circle. So we will have two circles here. And to do that, we will multiply the second equation by 2, and then we will have to subtract the second equation from the first equation. So we will have x squared plus y squared minus 2 times 3x plus 4y equals 100 minus 2a. And that is another circle. But to see the coordinates of its center, we will have to first turn it into a couple of perfect squares. So we have x squared minus 6x and also y squared minus 8y, which implies that we need another term like plus 9 to see a perfect square here. And also we will need plus 16 to have another perfect square here. Now if we added 9 and 16 to the left hand side, then we should add 25 to the right hand side as well. So we're gonna have 125 minus 2a. This, I hope you see that, is x minus 3 squared. Here we have y minus 4 squared, and it is all equal to 125 minus 2a. And now we're going to solve a new system of equations. We have this equation and the first equation, x squared plus y squared equals 100. So this is a circle with a center 0, 0, which we are already familiar with. And there is another circle with a center 3, 4. So its center is here, and its radius is 125 minus 2a under the square root sign. So the radius of a smaller circle changes depending on the value of the parameter, and we need such value of the parameter a for which the two circles touch at exactly one point. And let's first find the distance between the centers of these circles. Since the coordinates of these points are 3 and 4, then this distance is equal to 5, based on obviously Pythagorean theorem for this right-angled triangle. Now if these two circles touch at exactly one point, then this distance 5 is equal to the difference between the radii. So this is the radius of a larger circle, it is equal to 10, and this is the radius of a smaller circle, which is square root of 125 minus 2a. And the idea is that the larger radius minus the smaller radius is equal to 0,1, 0,2, where 0,1 is this point and 0,2 is this point. So we have 10 minus square root of 125 minus 2a equals 5. Now square root of 125 minus 2a equals 5, obviously. We square that and have 125 minus 2a equals 25, which gives us a equals 50. But that's not the only value of the parameter a for which this system of equations has exactly one solution. There is also that situation when the circles touch like this. And for that case, we're going to use that segment O1, O2 as well. But this time we have to subtract this radius, which is equal to 10, from the larger radius, which is equal to square root of 125 minus 2a. So we're going to have square root of 125 minus 2a minus 10, which is this radius, is equal to O1, O2, which is 5. So square root is equal to 15, and 125 minus 2a equals 225, which now results in a equals minus 50. And thus we have two values of parameter a, for each of which this system of equations has exactly one solution. So this system of equations has also exactly one solution. So that's another graphical solution, which is, in my opinion, more complicated than the two previous solutions. But we want to explore the relations between the solutions. And the relation is that if we consider these two circles, then their intersection points always lie on this line. So for instance, if we draw this circle like this, then we can draw this line like this through two intersection points. And that's the connection, that's the relation between two solutions. Now let's look at the solution number 5, which is entirely a new idea. We're going to use the derivative of a function here. So first we're going to turn the first equation into two equations of functions. We know that y squared equals 100 minus x squared, which gives us y equals square root of 100 minus x squared for all non-negative values of y, or y equals minus square root of 100 minus x squared for all the negative values of y. We will also turn the second equation into y equals minus 3/4 of x plus a divided by 4. And the idea here is to find such points on the graph of this function where the tangent has created minus 3/4. So we're going to find the derivative of this function, which is equal to 1 divided by 2 square roots of 100 minus x squared times minus 2x. And we're going to say that it is equal to minus 3/4. So we have an equation x equals 3/4 times square root of 100 minus x squared, which means that 16x squared equals 900 minus 9x squared. So 25x squared equals 900, or x squared equals 36. And x is equal to 6. Because x equals minus 6 is impossible, because it contradicts this equation. So for x equals 6, we find that y is equal to square root of 100 minus 36, which is equal to square root of 64, which is equal to 8. And now we can find the value of parameter a, just plugging these values into this equation. So we're going to have a equals 3x, 3 times 6, plus 4y, 4 times 8, which is equal to 18 plus 32 is equal to 50, which is not surprising. So that's the first value of parameter a. Here we're going to have almost the same derivative, except there's going to be a minus over here. So we're going to have minus 1 over 2 square roots of 100 minus x squared times minus 2x should be equal to minus 3/4. So we're going to have almost exactly this equation, except for the sign of x. So it's going to be minus x equals 3/4 times square root of 100 minus x squared. So we're going to have exactly the same solution because we just square both sides of this equation. But this time we're going to say that x is equal to minus 6 because the positive value of x would contradict this equation. For x equals minus 6, we will have y equals minus square root of 100 minus 36, which is y equals minus 8. And a will be equal to 3 times minus 6 plus 4 times minus 8, which will give us minus 50. So once again, we have two values of parameter a for each of which this equation has exactly one solution. And this time we proved it using the derivative. Now let's move on to the next solution. Now the idea number 6 is using trigonometrical substitutions. So we're going to use trigonometry. We're going to let x be equal to 10 cosine t and y be equal to 10 sine t, where values of t are in this interval from 0 to 2 pi. Now the first equation turns just into the main trigonometrical identity, which is cosine squared plus sine squared equals 1, which we can obtain if we just divide this equation by 100. So that is true for any value of t from this interval, which is why we can use that substitution. The second equation of the system now turns into 30 cosine t plus 40 sine t equals a. And here we can use the so-called auxiliary angle method. Maybe you call it some other name. By the way, write down in comments how do you call it. So we will have 50 cosine t minus alpha equals a, where alpha is equal to arc cosine of 3/5. Now, we want this equation to have exactly one solution, because any t from the interval is a solution of the first equation. So the whole system has as many solutions as this equation. And when does this equation have exactly one solution? Only in cases when the cosine here reaches its maximum or minimum value, which is 1 or -1. So a should be equal to either 50 or -50 in order for this equation to have exactly one solution. So here we have the two values of the parameter a. I personally like this solution very much because it's very elegant, and also you have to demonstrate some creativity to come up with this idea. Now let's move on to solution number 7, using vectors. We can think of these two equations as of something that describes two vectors. Vector p with coordinates x, y, and let's say vector q with coordinates 3, 4. Then equation 1 defines the length of the first vector. So modulus of p equals square root of x squared plus y squared, and it equals 10. And equation 2 here is nothing but the dot product of these two vectors. So we have p dot product q equals x times 3 or 3x plus 4 times y, and it is equal to a. We need to find the values of the parameter such that there is a unique vector p whose dot product with q is equal to a. But wait a minute, we can also write the dot product as modulus of p times modulus of q times cosine gamma, here gamma is the angle between the two vectors, equals also a. And we know that this is equal to 10. We know that the length of the second vector is 5, obviously. So we're gonna have 50 cosine gamma equals a. So once again, we have a trigonometric equation which has a unique solution only when a equals either 50 or -50. The geometric meaning of this solution is that the angle between 3, 4 and vector xy should be either 0 degrees or 180 degrees for there to be exactly one vector. Because if the angle is, say, 60 degrees, then I can draw two vectors of the same length, here and here, making that angle with 3, 4, both giving the same dot product. So in this idea we used vectors. How about that? Now let's consider solution number 8, the wildest one. And I'm pretty sure you didn't see this coming. We're going to use symmetry. Here's the idea. Notice that if we substitute x and y in the equation with a pair of numbers -7x plus 24y divided by 25 and 24x plus 7y divided by 25. Wait, don't close the video yet. If we substitute x and y in the equation with that, then the equation remains unchanged. We're gonna have the same equation, there's no change. Let's prove that. Let's plug that into this equation. We're gonna have -7x plus 24y divided by 25 squared plus the other fraction squared equals, and now let's use the square of the sum formula 2 times. We're gonna have 49x squared minus 2 times 7 times 24xy plus 576y squared plus the same thing for the second fraction. So we're gonna have this. We're gonna have this. Now this is all divided by 25 squared. So there is a big fraction with a denominator 625. Now these two terms cancel each other. So we just cancel them. Now notice that 49x squared plus 576x squared is equal to 625x squared. And here we also have 625y squared. We divide all that by 625 and we get x squared plus y squared. So we had that equation, x squared plus y squared equals 100. We substituted x and y with this, and now the left-hand side of the equation remains the same. There is no change. That means that for every solution pair x and y, there's another solution pair, which looks like this. But we want a unique solution. We want exactly one solution, which means that x should be equal to that fraction. So we're going to have x equals -7x plus 24y divided by 25, and y should be equal to that fraction. So our new system of equations is this, and y equals 24x plus 7y divided by 25. And by the way, I should have proven that this equation remains unchanged too, but that's going to be a simple proof, so I'm going to leave it to you. Just substitute x and y with this and see yourself that the result is the same equation. So we just have to find the solutions to these equations. So we're going to have 25x equals that and 25y equals this. And both of these equations give us the same result, 4x equals 3y, which we should plug into the first equation, which will give us the values of x and y. So if I say x equals 3 over 4 times y and plug it into the first equation, then I'm going to have x squared, which is 3 over 4y squared plus y squared equals 100. And if I solve that equation, I will have y equals plus or minus 8, which gives me x equals plus or minus 6. And we already saw in one of the previous solutions that if x equals 6 and y equals 8, then a equals 50. And for negative values of x and y, we're going to have the negative value of the parameter a. So once again, we have a equals 50 or a equals minus 50. And we have that result using symmetry. Now, how do you come up with a solution like this? Let's be honest, you don't. You don't just look at the problem and invent it on the spot. The problem itself doesn't suggest such a method because there is no symmetry in the coefficients. But the idea exists, and you can, in principle, find such coefficients for x and y that make this symmetry trick work. And in this case, notice how 7, 24, and 25 are a Pythagorean triple, as well as 3, 4, and 5. And if you look closer, then you're going to notice that the angle of a triangle with legs 7 and 24 and a hypotenuse of 25, this angle is the half of the angle of the triangle with 3, 4, and 5 as its sides, which is curious. So there's plenty of math underneath this method. So how do you like this method? Write down in comments. And let's move on to the next one, to the last method. Now let's look at the last solution of this problem, number 9. It includes a counterintuitive move. We actually need to make the problem more complicated. So in this solution, we're going to consider a cylinder. So how do we come up with a cylinder? Imagine that the parameter a is actually the third variable. It's the height. So let's call it z instead of a. Then the first equation defines a cylinder in 3 dimensions. The second equation, 3x plus 4y minus z equals 0, defines a plane. Now let's look at these surfaces in Desmas 3D. The first equation defines a cylinder. If we look at it from the top, then it's just a circle with radius 10. X squared plus y squared equals 10 squared. The second equation defines a plane. And we can see that the intersection of this plane and the cylinder is some ellipse. And this ellipse is formed from all the solutions of the system. Now here comes the key insight. The values of a or z, which is the height, for which there is a unique solution, are the maximum and minimum of this ellipse. So they're at the top and at the bottom of the ellipse. And these extreme points lie along the normal vector to the plane. That is, along the direction of the vector 3, 4, and minus 1. Now going back to the two-dimensional plane, the projection of this direction gives us the line y equals 4 over 3x. So we have y equals 4 over 3x. We use substitution in the first equation. We have an equation which looks like this, equals 100. And we get our two solutions, 6, 8 and minus 6, minus 8. We already know that the values of parameter for each of these solutions are a equals 50 and a equals minus 50. So that is the final 9th solution. We had to consider a cylinder and a plane. This is a very beautiful idea, but it requires extra thinking. So thank you for watching this video. I hope you liked it. I hope you learned something new. And if you did, then please consider subscribing and writing some comment to support the video. See you in the next one. Bye.